Welcome to the Bobby Soxer Show, the podcast where nobody gets left feeling shocked, with your hosts, Ashley Patterson and Alan Mustafovsky.
And we're back. I had to hit play on hit the record button on the second camera or my main camera, but I got to figure that out, because it just records in 28-minute intervals and it just keeps interrupting. And we're also having other technical issues. There's no technical issues.
To see what we're recording.
But if you have been sticking around so far, Dr. Peter has been going through how we started in, I guess, computational chemistry. And we're just pretty much going to lead in from there.
Wonderful.
So how long does it, when you found out that you were led down the road of computational chemistry, what's the process of that? Is it just a standard 4-year degree, or how does that work?
So to go from, I guess, out of high school into right now assistant lectureship, first of all, there's a bit of luck that kind of permeates through it, as there always is, favourable circumstances. But yes, so there is that 4-year degree of the bachelor plus honours in science, and that's if you're doing it full time. If you're doing it part time, it takes a bit longer. And then after that, I actually did take a 6-month break to kind of decide where I did want to do my PhD, because I heavily considered going overseas for that, because I think during my honours degree, I actually did go overseas for a bit of like a research exchange. Mm-hmm. So. Yeah, I guess I was kind of given opportunities to potentially go overseas as well.
If we can ask, where were you considering going, and why was that such a contender in making your decision?
Yeah, so I really enjoyed the idea of, I think, maybe just being abroad. In general, I felt like I'd spent maybe, at that point, it was 23 years in Australia. I'm like, I could definitely do it for change. But then abroad would have been most likely in Germany. To do a PhD. Otherwise, the UK was also an option as well to consider.
Could have gone to Wimbledon, bro.
Could have gone to Wimbledon. I know. I want to go one day, but I think it's like a ballot system, isn't it? It's like a random lottery that you have to sign up for and stuff. Yeah, it's brutal. Yeah, but one day. I mean, bucket list for sure. I want to go see
strawberries and cream.
Yeah, that's it.
Keep hyping it up. So
yeah, I mean, look, Melbourne is so lucky to have the Australian Open. By the way, it's insane. But yeah, so going back, it was also back then perceived to be favourable to, and maybe it is still perceived to be favourable to kind of do your degree somewhere, do your PhD somewhere else, do your postdoctoral research somewhere else as well, just to kind of show that you're independent in your research and you can hold your own weight and carry your own kind of research direction.
Right.
Yeah. So that's why those were, I think, were the two main considerations. For whatever reason, I don't know, maybe myself six years ago just felt like they wanted to just go abroad and just spend a lot of time overseas. But now, as circumstances have led me, I started my so actually my PhD was supposed to be a joint PhD. So I was supposed to spend a year in the UK as part of my studies.
Wow!
But thanks to a little known virus known as COVID, I had to stay in Melbourne for the duration of my PhD. And I still ended up with a joint PhD between Monash University, University of Warwick. Thankfully, I was able to kind of argue my case to say I still contacted my UK supervisor for quite a while, very very regularly and whatnot. So I still held that joint PhD, which I think helps. But so that started in September of 2019. Mm-hmm. Submitted my thesis in 2024, and then. Sorry, I just got a phone call. That's all right. And then what was I going to say? So
PhD 2024.
PhD 2024, and then so that's kind of like the progression of degrees, where you go from undergraduate, so then your PhD, and then after the PhD, there is kind of, you're supposed to do postdoctoral research, which I kind of. My assistant lecturer position kind of feels like that a lot. Mm-hmm. But after you do a postdoctoral position, then you kind of go towards. That's when you go for that lectureship position. So, assistant lecturer is kind of like the very first step, very first rung of the academic ladder. Mm-hmm. There's a lot more. You can become a lecturer, senior lecturer, associate professor, professor. That's kind of like the ladder.
Is that anything you're aiming for there? Or you're happy with where you're at the moment?
Well, you can't really stay in this, like...
Okay, so you sort of have, like, there's like a...
It's a bit of a funnel process where...
Okay, gotcha.
The higher you kind of go, you are expected to kind of progress towards the next step as part of academia. You can't really settle, I think, here.
Is there a time frame for each one, or like what's
there's like kind of like an implicit one, right? So it's this kind of
like passive aggressive. Like you should probably be moving on, Pete.
So because what happens is that like the opportunities kind of dry up if you don't really move. If you don't really like show that you're progressing, then unfortunately opportunities dry up. Yeah.
I was going to say, like, is it more along the lines of like, they see you and then they see someone else and they're like, well, if you're happy where you are, then this person's going to rise among the ranks.
That's right.
And then like, if you want to move up, you're going to have to wait for this guy to, sort of like implicitly saying, get your butt off the ground. Like it's now or never sort of thing.
That's right. So I think that's right. There is like, in terms of academia, there's like limited positions and a lot of people.
Yeah.
So it is actually highly competitive in that regard. So
I guess going back to maybe like a little bit about your work. So where does like you finish your degree? Where do you go from there? Like, what kind of jobs say like I've finished my degree? Like, what's the job market like? Where do you go to like work, for example?
Sorry, can you say it in terms of
I become a computational chemistry person. Right. So what's my job market like?
Okay, so actually in research, at least in our research, we become very qualified like data scientists and data analysts. So there's a whole bunch of industries. So I think people with similar kind of experience would go into, say, like maybe they work for like maybe insurance firms to like work with the big data there. I've also heard just being like as a general data analyst for whole different kind of companies, like marketing companies and whatnot. So there's also a lot of programming experience that comes into it.
Okay,
and you can also kind of enter more chemical firms as well. So
okay, cool. So it's not just like you finish and then you go, okay, I'm just going to become like a lecturer because this is what I'm. There are actual like. There is a market because I was just said in my head, I'm like, okay, you're sitting behind a computer all day. Like, what do you do in terms of like compensation? Now, I have like a little bit of a question that goes in maybe a weird direction. In terms of like, because you do computational chemistry, like, can you make your own cryptocurrency?
Look, in terms of making it, I mean, you would probably possess the programming knowledge to do that if you really wanted to. I don't know specifically myself how to go about that, but I imagine with your ability to do computational chemistry, I think you would be pretty capable of researching and finding out how to do so.
I was just sort of in my head, I'm like, if you're crunching numbers all the time, you'd probably be like, I can figure this out. And
well, I think one part is to launch the cryptocurrency. It's another part to make people want to get it, right? That's the whole other part. Like,
if you make it exciting enough,
that's a marketing thing, isn't it?
Yeah, exactly. Like you could make all the data around it, but you need, I guess, a front face to be like, this is, the cryptocurrency to buy. But I guess in sort of that realm, like when you were growing up, and maybe what led you down to this path is that were you a very logical person when you were growing up, or so like you're like this is obviously science, math, and all that stuff. You go okay, well, because I was like growing up, like English was my jam, like for the life of me, math and science were just not coming to me. And I'm like, man, I did like. I think physics like 1 to 4 and like further maths and special and math methods. And I'm like, man, none of this is working. So I very much had a creative brain than more than a logical brain.
Yeah, no, I think I've definitely spent a lot of time trying to just find the logic in things and how they work. So even languages, I think I actually, well, due to my parents being Polish, born from Poland, I do speak a bit of Polish. And so I speak a bit English as well, but I really enjoyed studying Japanese in high school as well because I thought there was a very logical flow to that.
Yeah,
but I mean, I think it's just the way different people, I guess, are wired and grown up. So yeah, I think I definitely lean heavily more into like the logical way, and I kind of, when I see a problem, I try to like break it down logically. And I will say I have indulged in my kind of creative side a lot. I think it's really important. I really enjoy the mindfulness aspect of say like doing some kind of cross stitching or just like even just sewing. Just like I don't know. Yeah, I definitely have indulged in my creative side. I think, especially since COVID. Yeah.
Okay. Well, like I said, that was like sort of leads me into another thought of like, what are your hobbies? Like, do you like? What are your hobbies other than obviously you got tennis, but does your computational mind or the mind go breaks down the hobbies in different ways, or like how does that work for you? Like if you like go, I'm playing tennis, and does you like, don't I know it's typical for me to say like if I hit the ball at 90 degrees and like in his forehand, he's not going to be able to hit it. You know, that kind of thing.
I would say there is a bit of calculation going on, like in terms of what I think my opponent can or can't do.
Yeah,
but it's really in terms of the specifics. No, I mean, the human brain, I think, in that regard, especially when it comes to sports, it is calculating all these numbers and angles and stuff just in its own way.
Yep.
Like, and to kind of abstract it and try to like put it out into equations, I think is taking away from what the human brain's already doing.
Okay.
So, you know, if we're talking about mathematics, you may have heard of like, maybe you're scared of like the word of like, say, calculus and stuff. Or, it's a scary word. But whenever you're playing tennis, or like whenever Alan's playing tennis, like the human brain is just calculating, oh, where's the ball going to be at this amount of time? That allows me to wind up my shot. So our brains are already doing calculus in their own way. And it's like, it's just a way that we just don't really, I think, maybe appreciate.
Yeah,
so,
that's fair.
Yeah.
I've just got a few questions that I need to get off my chest.
Off your chest?
Yeah, because there's only a certain amount of time, and I want to get into this computational thing.
Oh yes.
Yeah. What's the coolest thing that you've worked on so far as computational chemistry?
Yeah. So computational chemistry, you can kind of, a bit about the scene is that, you know, we have access to the whole periodic table, really. So, I mean, I think last year I published a paper to do with some silver work, which I thought was really, really cool. So I really enjoy the fact that I can kind of explore the periodic table and look at how different chemicals behave from that periodic table. So, I mean, I've done so many, I think, things that I find to be really, really cool, honestly. So, I mean, I'm even like using a bit of machine learning in my work. I think
the whole machine learning is a whole nother rabbit hole, isn't it?
It's a whole other paradigm, really. Yeah. And something I didn't do during my PhD, I was used maybe sort of what we call more traditional methods that are kind of expensive. We're using up like, you know, nodes of a supercomputer to crunch away, but machine learning can really make our work so much quicker. And so that's what we're kind of we're tapping into, trying to make it accurate enough for us to work with. But yeah, sorry. So the question was like, what's the coolest thing I kind of have worked on?
Yeah.
It's probably
don't worry if it's too nerdy. Because if it's cool to you, that's what's important.
Well, I appreciate that. That's such a cool thing. I think I'll just shout out that work I did last year where we had like you had like a silver, and then silver like say atom here, and then you had like some tweezers come out of it. So we actually formed like tweezers with like a metal in the center, and like the fact that I could appreciate what this silver atom and like all of its like little tweezers could do like at like an atomic scale, right? So, you know, that's what I think is really cool about computational chemistry. We're going from the ground up.
Yeah. So has all this work changed the way that you've looked at the world every day? Because now that you're seeing things on a different level or a different scale or magnified or whatnot, are you looking at the camera or a chair a little bit differently, or like, is it like a Matrix thing where you see
I will say I don't really see the thing with solids.
Not literally, but
But the thing is, my work specialized in simulating liquids and how liquids behave. So my PhD thesis was actually about how do we simulate liquids that will make lithium-ion batteries safer. That's like kind of my thesis title in a sense. So whenever I see like kind of like liquids maybe interacting, I try to like visualize. Oh yeah, what's happening there? Because you know I've done simulations where we've made like buckets of molecules, and we see all little molecules move around and do their own little thing.
By the way, how accurate are these simulations?
So there's always a compromise always between accuracy and cost, because if you want to use all the laws of physics and treat them properly, it's very, very expensive very quickly. And you can only do that up to I'll say chemical systems the size of up to like even like 20 atoms. So we understand. You guys know it. Like as in, for atoms, like we're talking like that's only like a few molecules.
Yeah.
So you can only really treat like a few molecules to like a really, really high level. If you want to start getting more towards like a bucket of molecules, that's when you have to make some shortcuts. So the shortcuts is that well, this is something I kind of maybe perhaps wanted to bring up was the fact, because if you visualize like an atom and a molecule, you know it's made out of like protons, neutrons, electrons, right?
Yep.
I've heard of all that.
You've heard of that? but
heard of these
when
three
you were
words.
taught of these things, you're taught of like electrons being particles, right?
Yep.
Yeah.
Whereas in reality, which is also what's important about quantum mechanics, is that it turns out electrons, because they're moving around so quickly, they actually become more like a wave, and they're more like actually kind of spread out. So, so if you kind of think of like your traditional water molecule, hydrogen, oxygen, hydrogen, and the electrons, maybe you might think they're whizzing around each center. No, in actuality, your electrons are kind of forming a cloud around the molecule. And that's kind of one of the underlying things of like quantum mechanics is that, well, things that we think of like as particles, at the really, really small scale, they can actually exhibit what's called this wave-particle duality, where they become more wavy.
And you've seen this like on a, like, is there anything that...
Yeah, you can visualize it.
Yeah.
So you can visualize just like these electron clouds on top of molecules.
But you don't have just say like a simulation or something that shows these electrons or anything like that? Or?
No, I think it's actually an important part of research is to identify where the electrons are sitting in a chemical system to see like why they're reacting. So, you know, obviously a reaction is when two molecules come together and they either form a new bond or they don't. And looking at where the electrons are and like or where their clouds are can really inform you as to why or why not the reaction will happen or not. So that's a chemical problem that I might solve in my research.
Okay.
So I told you this was going to be interesting.
Yeah, I know. As we delve deeper, and you're asking the right questions, so
I'm trying. I've got limited capacity. No, this is awesome. This what's the most rewarding part of what you do?
Yeah, I think I just really have an innate thirst for just kind of like knowledge, you know, and like kind of I really enjoy the fact that I'm seeing how the world behaves at like that really small scale. I feel like it's just such like
it's kind of a world within a world within a world kind of.
There's so many layers of abstraction between what we're doing now and like what we're you know, and like what's happening at that really small scale. So I think that's the most rewarding part. And also in research, you are contributing towards like the edge of human knowledge, right? Like the work I'm doing is new. No one else has done it before. And we're answering questions that, you know, we think will help inform those who decide to do more research
that
in the future.
in itself is a crazy concept because like you'd think with how far technology has gone and how you think everything's been done, but what you've just said, all this stuff hasn't even been discovered.
So if I were to talk about human knowledge like a balloon, if I may. Yep. So if you imagine a balloon of human knowledge. 2 centuries ago, you hear about the absolute legends, mind you. Like the research I'm doing is off the back of like, you know, centuries, if not millennia of like research from those before me. But, you know, if you think about like if you start inflating a balloon, you can still kind of like see the other side of the balloon maybe. But as you inflate that balloon, so if you inflate that balloon to coincide with like how much more we've learned, then what it means is that on the surfaces of, if you like kind of maybe, you know, you've drawn like a smiley face on a balloon before, when you blow it up, it gets further apart. Yeah. And that's what's happening with our knowledge as well. The knowledge is getting more and more specialized and it's more and more further apart. And it means that it's actually harder to kind of grasp everything that's happening in the research world. So,
Okay. I guess it's like, on that, is there, like, do you think in your line of work, do you think you'll ever you'll hit a wall and go, okay, this is maybe as far as we go because of limitations of technology, or do you think that might come up, or you go, okay, this is it, and then we have to wait another 20 years for the next guy, come around?
Yeah. No, I think there's always... Technology is a big limitation of our work because computational chemistry, computers haven't been around for that long, right?
Exactly.
This field didn't exist 100 years ago, but it's existing now, and we're permanently trying to push the barriers of what our technology can do because the physics is there. The laws of physics are there. It's just a matter of bringing that up to all the problems that we want to solve. Yeah. So I'm actually, in my work, I'm kind of bridging between that really complicated physics and trying to get trying to draw the answers out of it.
What are the main problems you're trying to solve?
Yeah, so if anything, so we know I spoke to you about computational chemistry is about solving problems. So if I can go one level deeper, there's actually like a bit of a meta-analysis about that, where I'm actually kind of critiquing the current techniques that are used for these predictions.
Right.
And how to make them even more accurate and how to make them even more cheaper. So when we talk about machine learning, and I've spoken to you about electrons as well. So we think about these electron clouds. So it turns out, and this is what a Nobel Prize was given out for a couple decades back, but the theories came out in the 60s. There's a theory in the 60s that says, if you know where the electrons are around your molecule, there is a way to calculate its energy. So energy meaning like how much power you need to like pull apart the electrons from that molecule. There is a mathematical relationship between these two things. They prove that it exists, but we don't know what it looks like. And over the past 50 years, scientists have been throwing the kitchen sink of mathematical formulations to try and figure out what this relationship is. And my work is partly to do with trying to machine learn that relationship as well. Because we know it exists, we just don't know what it looks like. And again, as technology gets more and more better, these big companies are buying out a whole bunch of GPUs to fund the different
You're
things.
responsible for the prices of.
And actually, so I was going to say, I didn't want to say my work. Notice how
much I had to pay for that piece.
I was going to say, I have to tell our clients the same kind of thing. Like, your laptop's gone up 40% because of people like this guy.
How expensive this podcast is produced.
And that's the thing. So notice how I said machine learning and not AI, because generative AI is, I do like to say that what I'm doing is more, AI is more about generating kind of data, whereas machine learning is about solidifying data and compressing it into
you're
something.
Cool then.
He's part of the cool crew.
I'm not biased. If I may say so myself. I think I'm cool.
This cool crew is going to end this part right here, and we'll be back with the next part. And we're back, everybody. Thank you for joining us. We've got the lovely Dr. Peter still with us. He decided that, we're still cool cats. So Alan still has a few more questions to ask Dr. Peter. And kick us off.
All right, we'll knock these out of the way, and then you said you had a couple stories.
I have a couple kind of science communication stories I want to maybe float by you two and see how it lands.
Yeah, cool, man. Hold on to that. What's the hardest part about your job? What's the most what are the challenges? I mean, you kind of mentioned it, but I guess.
Well, the thing is, I spoke about research. There is also another aspect where I also do a fair bit of lecturing too, right?
Yeah, the lecturing thing, that was going to be like a whole separate section. We've got so much to talk about. We got to get you back on.
I would love to be back.
Yeah. All right, cool.
Yeah.
Most challenging thing about the lecturing, the computational chemistry.
Yeah, it's really hard to determine where to focus my time and energy, honestly, between research, lecturing, and obviously as you kind of immerse yourself within a research sphere, there's a lot of networking to do. You go to conferences, you kind of you communicate a lot as well.
And then you got the whole club thing on the side as well. You do so much, man. Very impressive. I'm impressed, by the way.
Well, thank you. Well, the thing about that is I do everything that I want to do. So if I don't want to do it, then it just it doesn't work out for me. So, and I think that kind of goes with a lot of people, right? If you're not doing, if you do something you hate, then it's just But okay, so in terms of lecturing, researching, I think it's about balancing it all and being careful not to get caught up with some things, because the thing about research is that we spoke about limits and stuff, but from my perspective, there's so much that you can do in research. There's so many unanswered questions out there still that we can solve, especially in chemistry. Sure, we talk about 100 elements in the periodic table, but when you start combining them, there's just so many different ways to construct a molecule, and therefore so many different things that we can test out. So I think for me it's about being careful not to let say research consume you, really, because there's you can research as much as you like, but there's no closure really yet.
Yeah. Oh, perfect. If someone wanted to get into your field, what advice would you give them?
Well, I think as with anything, get a taste for it early. Just give it a try. So I was very fortunate in the first year of my degree to conduct research in this field. So that's something that I would recommend for any budding undergraduate students, or even just anyone going through school. Like, really, just if you're not sure about doing something, see what you can do to give yourself an experience in that as well. Take on an opportunity to get some experience, and then you know for yourself.
Mm-hmm.
Cool. Yeah, is the whole assistant lecturing thing what you imagine it would be? Yeah, and are there any skills in as an assistant lecturer that you've transferred over to other areas of your life?
Yeah, well, I think you talk about doing working with the tennis club, working as an assistant lecturer. I kind of think that all this stuff does benefit in many more ways than I kind of realized. So, going back from high school, I don't think I was the best maybe public speaker, or at least I felt like I would actually be very nervous about speaking publicly.
So would you consider yourself more of an introvert?
I'm absolutely an introvert,
Okay, yeah.
But I really do enjoy kind of networking and connecting with people. But at the end of the day, after a long day of speaking, then I kind of find myself at home kind of wanting to just, bit of me time and just kind of in a kind of introverted way, right?
Yeah. You need to charge.
Recharge the batteries, that's right. So you either recharge your batteries by talking to people, or you recharge your batteries by that's kind of one way to kind of, to determine if you're introvert or extrovert, right? But yeah, after a lecture, I need to chill, relax, because it's 2 hours of pretty much straight talking. So definitely need to relax after that. But yeah, so what I'll say is that I think, when it's maybe when it came to say during the pandemic, when I kind of spoke with a lot of people online community, that actually really helped my ability to speak publicly, I would say. And even I think at the tennis club where I meet a lot of people, I kind of get to know a lot of people. That actually transfers really nicely into academia as well, where you have to constantly, I don't say you have to, but it's in your best interest to get to know a lot of people doing cool research to set up future collaborations for yourself. So I really do try to find the value. And I genuinely think that everything I do does benefit me, gives me experience in a way that I can use across all facets of my life.
Brilliant. I think we can get into one of your stories now.
All right. So I'm going to give you a thought experiment. So let's say Alan's on a tennis court serving a tennis ball. Maybe I don't want to put you under too much pressure, but how
feel the gravity of
no. So it's a simple question. So how quick do you think your serve is typically?
That's weird. That's a tough question because sometimes I think it's quicker or slower than what other people say because. The serve thing's a funny thing because your perception of what you think you're doing is totally different to the outside. And I suppose that's why everyone gets coaches.
Yeah, right. So, exactly. They're true. And actually, if we just a little
I could not tell you what, let's say the first serve, I couldn't tell you. Well, if I just tried to smash it in,
Let's say Alan smashes the first serve 150 Ks and Ash, you're there, you're standing next to Alan. You see him smash the ball at 150 Ks per hour. Great. Now let's imagine that Alan's now in the back of a ute, and he's going to do the same thing. So the ute's going to drive in a direction, and then Alan's going to do a serve on top of that.
I know this what you're going with.
Yeah.
So
right.
you might be directed to Alan for this one.
Yeah. Okay. So you know where you're going. Okay.
I know the experiment.
Okay. So if you're on the back of the truck and you serve it, and Ash is sitting there. So let's say the truck's doing 100, which obviously very unsafe. Please don't do this unless you're
disclaimer.
Unless you're filming an episode.
Because there are people that would try this.
Okay, cool. So Alan does this. So you're on the back of a truck that's doing 100, and you decide to do a first serve on the back of the truck. What speed does the ball? What speed does Ash see the ball coming out of your racket from?
Oh, actually, this is a bit different than I thought. But so I would say if it was doing 150 normal, the truck is going 100.
Yep.
I would say, but in the other direction.
No, it's in the same direction, so it's adding onto it.
Oh, right.
Yeah.
Oh, so he's coming towards me.
Oh well, I think ideally you're at the path of the truck. I would hope. But the truck is adding to Alan's speed.
Okay, but I still like my thought process. I mean, you'd say, "Oh yeah, it's going like 250." I don't think it's going 250.
Okay.
I think there's a lot of vectors that calculate into it, but I would still say maybe 200.
Okay. So where you're going you're actually spot on the right track. So, because now we want to talk about like the same experiment. Because at the speeds of 100 and 150, they're not close enough to the speed of light to make a difference. So in these speeds, I think you would still observe Alan serving at 250 k's.
Yeah.
But let's do the same experiment, but like with a torch. So Alan, for whatever reason, decides to shine a torch out of like the baseline of a tennis court, and you're measuring the speed that light comes out of that torch. Mm-hmm. And now, and the speed of light is, at like 300 kilometers per second. So, So that's right. So, actually, wait, let me make sure I've got that right. Yeah, 2.99 meters. Yeah, so that's right, 3,000 kilometers per second. So, when that happens, if say Alan's like going on, is it now on the back of that truck, and then you shine a torch, the thing about light is the speed of light is the exact same in both scenarios.
Okay,
so no matter how quickly something is moving, you see the light moves at the same speed.
Yep.
So that's different because with the tennis ball serving scenario, there is a difference in the speed, but the speed of light is just this constant. So no matter how quickly you're moving, the speed of light is always the same. And so even if someone is moving 100 kilometers, so Alan on the truck, he'll see the speed of light moving in the same way that you're seeing the speed of light moving at the same way.
Yep.
And then, how do you make sense of that?
Yeah, well, that's what I'm about to ask you. How do you make sense of that?
And if you've ever heard of the word like relativity or like maybe special relativity, that's where it comes from. It's trying to figure out, okay, how do we make all of these people who observe the speed of light at the same speed agree? And so how that comes down to is that you have to actually distort time for different people. So I don't know if you've seen Interstellar.
Yeah.
So that planet that they're on, where every tick is like a year in Earth.
Yep.
It's because that planet is moving so much more quickly than Earth is, and so
Can I ask you a quick question about time? Because everyone seems to think time is moving faster after COVID. Do you think that, or do you think time has gone faster as you've gotten older or aged, or?
I think in terms of the laws of physics...
Is that a perception thing?
It's a perception thing, yeah. In my opinion, in terms of the laws of physics, time is just... It is kind of staying constant for our lifetimes. But in terms of perception, I think the older you grow up, the smaller of a proportion each year of your life is. So if you're turning 10, your last year was like 1/10 of your life. If you're turning 20, 1/20th of your life was the last year. I'm about to turn 30 later this year. This last year will be 1/30th of my life. So it's a perception thing.
It made it sound like it was bad.
Yeah, and I was like, you said that on the way.
We're going on to
man, I'm 1/4.
Yeah, so I think it's a perception thing. But the thing about time, though, it's we've pretty much invented how to keep time constant, because there are some chemical processes that just happen to occur at the same rate, and then we can all agree on that. But in terms of the laws of physics, time is just this progression of chemistry and physics.
Well, I kind of always heard sort of on Alan's thing. I've always sort of heard that that time's moving faster, but I think don't we have some sort of scientific research where we have gotten faster in terms of minutes or seconds, into maybe the speed of where we move around the sun or whatever it is. I know we have,
because days. I don't care what anyone says.
Here we go.
Days feel longer when you're a kid.
Feelings, no facts.
Try saying that to every woman out there. All right. Feelings do matter.
Feelings matter. No, absolutely, feelings matter, and that's for everybody. I would say.
Exactly. Say it's a doctor.
I couldn't help the joke. I couldn't help the joke. I'm sorry.
I'll stray away from the gendered aspect of that and just talk about for everybody.
Okay.
But
I can't help myself. I have to say something that really.
No. But I think Yeah, no, feelings, like in terms of your, like, how, because, in terms of memories that you preserve as well, like, I think it is just something about how our brains work, where it's like, we obviously cherish our childhood memories, how we grew up, because they are the most impactful parts of our life. So, yeah, I think it's more of a psychological thing where we feel like time's going faster, I would say.
Okay.
Yeah.
And you had a second story.
Ooh, if I can remember. Yes. Okay, so this is another thing about light. So, have you been sunburned before? Maybe not. Yeah.
Yes, Alan's definitely been sunburned.
So let's talk. I mean, and so how does sunburn work in your mind?
UV rays
Yep.
hits the skin.
Yep. Okay.
Skin doesn't like it.
So
Burnt. Boom.
Let's talk about. Okay, well that's true. We have light UV rays coming down, and then like causing sunburn. So then the question is, why does infrared light not also sunburn you?
Good question.
Yeah. Do you have any idea as to why?
Skin is like UV. You're a piece of crap, and what was the other one? Infrared.
Yeah.
Infrared. You're cool, bro.
Okay. Well, no, that's actually correct. So.
Whoa.
that is correct. No,
yeah.
You're spot on. So,
Okay.
because how I spoke about how we talk about electrons no longer being particles, they're like more like clouds that have more this wave nature.
Yep.
The flip side also happens to light too. Light also is just a series of particles as well. So if we think of this light coming through as like a wave, in reality what we're doing is we're being bombarded with, this would be like so many, like uncountably amount of like what we call like, if I can explain it, because when you think of light as like a wave, you kind of draw like the up and down sine curve, but you cut that up into a chunk, and light is actually just a series of these chunks of light. So what we're doing, we're actually being bombarded by like so many different particles of light. They're called photons. That's what a photon is.
Yeah.
Like a single little particle of light. And it turns out that UV rays, each little like chunk of each little particle, photon of UV, carries more energy than the infrared ones.
Right.
And so chemically what happens is that, well, first of all, I should maybe also say that you have UV, infrared, and then the visible light spectrum in between, right?
Okay.
So, and so there's this whole continuum of like how much energy each light particle has.
Okay.
Yeah. So, which radio waves, super duper low energy particles. Microwaves, they're getting a bit more energetic, but that's why we heat up our food with them, and you don't want to stick your hand in it because microwaves love exciting the water molecules inside of you. That will,
Yep.
So, so radio waves and whatnot. So, yes, question.
Yeah. Just like before this thought leaves my mind, who are the like scientists or, the geniuses that you've admired over the years? Even if it's not like...
Yeah, they don't have to be big names.
they don't have to be big names.
I have to say my supervisor for the past 10 years is like an amazing scientist, one of the smartest people I've ever met. She's, I've been an absolute... it's been really I think I've been very lucky to have her as my supervisor for quite some time.
Yeah, because that's the thing, right? Like, there are so many people in our everyday lives that almost deserve to have some kind of like plaque put up. But, you can't do that with everyone, but it's just like there's so many admirable people out there that you could give credit to, and that.
Well, my supervisor. Maybe if I name drop her, maybe I can. I will just say like.
No, it's up to you.
Yeah, I think it's for the public record that I've been working in collaboration with Professor Katia Pass from Monash University. We've been working together for 10 years, and I think it's a very, very, it's been such a wonderful collaboration. She's really taken on a mentorship role as well for me. And now she's really look, me and our other colleagues, we're just in awe of her and what she does and her work. So we're always learning from her, and she's been so generous in providing her help for us as well. So that's the number one scientist I think has definitely been influential. I think also growing up, there's been a few different instructors that have really encouraged me to kind of just pursue my own thoughts and kind of aspirations. So yeah, definitely during high school, there was a couple of teachers who were just give this a go. Just keep, I see you're interested in this. Just keep on going. And then obviously there's absolute legends from the past. So those who were, first of all, discovered quantum mechanics. So we're talking like Heisenberg, Einstein was there as well, Schrödinger, like Dirac.
All those guys were like rock stars back then.
Yeah, honestly,
yeah.
Absolute rock stars in the physics world. Like Richard Feynman, maybe you've heard of as well. He was he also was a very influential character that time as well. There's so many more people that I obviously have just maybe missed, but yeah, there's just a whole host of like scientists who, like I said before, their work inspired like my current work now. I could, but I think my supervisor, I think, definitely deserves like it. I think about the time when our collaboration will stop, and if I ever have to move on or somewhere else, like I actually just don't know how to most appropriately like recognize and acknowledge like this 10 years of mentorship that I've been given.
No, that's a fair point.
Yeah. But shall we finish?
Yes, I was going to say finish. Sorry.
Sorry.
Oh, sorry for
no. This is great. No, I really enjoy. Like, I'm also this kind of person where, like, if I have a thought, I want to say it before I lose it. You know?
Yeah. That's all I got to say. Yeah, I'm good.
Yeah. So if I just between UV and IR. So IR being infrared and UV being ultraviolet. IR, like the energy that each of those little particles carry. It's enough to it's not enough to break bonds, but it's enough to kind of like excite chemical bonds. So if you've ever heard about like chemical bonds like vibrating, they're getting more energetic.
Yes.
Then, so that's why when you have infrared, maybe you haven't done like infrared sauna or something, it's warm because what it's doing is just providing when the photons hits your skin. It kind of vibrates your molecules. It doesn't break them.
Well, okay. What is the goal of the infrared saunas? Because I've seen them around. I've never actually used them.
It's an application of direct heat. So really, it's a controlled amount of heat that permeates into your skin and your muscles.
Okay.
So
all right. Just need to clear that up.
Yeah, because if you think about when you're I'm not a licensed physiotherapist or anything, but if you are injured, you try to like either you put ice on it or you put heat on it, just to kind of like help the blood flow. And a heat pack is just like a really surface level way of applying heat to your body. Yep. But IR can permeate even deeper.
Right. Okay.
Yeah. And so remember, we're talking about light being like a whole bunch of particles. And if a whole bunch of particles hits the skin, some of them interact with the skin at the surface level. Some of them maybe go through and keep going even further. And this is where ultraviolet light comes in. So we have infrared light. Then you have the visible light spectrum starting from red, and then another cool acronym maybe to learn is like it's called ROY G BIV. So it's like red, orange, yellow, green, blue, indigo, violet, and then we go ultraviolet. And the energy carried by again this like collection of photons hitting your skin. If it's ultraviolet, they're breaking chemical bonds.
Oh.
And it's causing damage to your skin and like DNA damage. And then chemically, when we're talking about having a tan or different skin colors, the skin color is determined by like a melanin, which is actually very capable of absorbing those high energy photons and just processing it and dissipating it before it gets to your, say, DNA or something.
Fair. Yeah. Well, I guess that sort of then goes, I guess, like down to the physiological aspect of like, someone like myself, like, I guess I'd love to know, I mean, you'd be going back to like, the dawn of time sort of thing, like what made us so different from between like, why I absorb more melanin than you guys.
UV, yeah.
Yeah, UV, yeah.
Well, look, I think it really comes down to the amount of, because, we talk about, you've heard of the ozone layer, right? So that is actually the Earth's first protection against UV light. So ozone actually interacts really well with, obviously, so we're talking about this bombardment of photons. The ozone, there's a lot of ozone in the outer atmosphere, and that can actually soak up that UV before it gets into Earth. But obviously that UV index that you may have studied is very different at different parts of the world.
Okay.
So as we know, and obviously we're on the lands of the traditional owners of Australia. As you know, they have a lot darker skin.
Yep.
And that's because in Australia the UV index can be quite high, and it's why for us with lighter skin we have to definitely be careful of putting on sunscreen and stuff. Yeah.
Okay.
So it's more of a evolutionary adaptation.
Right.
But also what I'll say about evolution is that this is something that blew my mind when I was an undergraduate student that I learned from a biology student. They said when they told me like evolution is actually not goal oriented, it's actually just a game of chance, and whatever succeeds the most just passes through. And so in terms of like, evolution, it's just like DNA mutates every so often, and there's mutations. They may change the color of your skin to adapt, and then whatever adaptations that suit the environment the best, they're more successful, and they end up, obviously continuing to live longer and breed more and so on. So
it's just it's a series of accidents that just happen at work.
exactly, especially at work. Yeah, but yeah, so. Yeah, hopefully, I think. Does that answer your question?
No, it kind of does, because I just sort of thought of what exposes us more than other places, and I guess I my head doesn't automatically think of like Aboriginal, because I just think like me.
Yeah, but I
know.
But I also wanted to kind of give an example, because like in Australia, like
I forget that. I mean, more central Australia is very, I guess, like heat prone, but. Being Melbourne all my life, I think of it more as London than I think of like heat.
Yeah, well, that's it. Right? In London, the UV index is so much lower than it is in Melbourne. I think, this is something I'm going to look up later for my own interest, is like the UV index comparing Melbourne and London, because in London, I'm sure it's so much lower, and I just want to...
I would say so, but like we are... I just sort of look at it and I'm like, man, we're cloudy like all the time.
Yeah.
There's like maybe 2 months where we have like pure sun, but then the rest of the year it's a write-off.
Yeah. So that's it. Yeah. So that's it. And it's just evolution. Decided that evolution, just random chance, saying like, oh, okay, those that have more melanin in their skin to absorb those photons, those UV photons. I was like, oh, they're more successful. So, yeah.
Fair enough. Are you done with? You'll finish up your questions?
Yeah, we got more than anticipated.
That was amazing. I now, like, when we obviously have you back again, I need to now write down a bunch of questions, because I didn't know like what to really expect going in. So now that I know what kind of stuff to expect, I'm like, okay.
It's a stark contrast from Ron. I don't know if you guys have seen that episode. I love Ron, by the way. He's the opposite.
He said, "Look, we love Ron too. I love Ron too.
Yeah, he's coming back as well." But
it is a
Dad
start.
was saying he was like, what's that guy? Tom Green.
Yeah, and I just sort of look back and I'm going. Unfortunately for him, though, we surprised him with the fact that we were giving him unsolicited advice. Unlicensed, unsolicited, unread.
No, it's cool though, because like we've got, like, it's almost like the guys that we've had on so far. We've got like a category for everything now. Like we've got Ryan, the spiritual guru.
Yep.
We've got like our own Neil deGrasse Tyson.
That's high praise. Thank you.
And then we got Ron.
And then you got Ron.
And Dan's just like a larrikin, like his
I
goal.
think Ron and Dan could be almost the same. Like
We got to get
category.
We will get them. You know that they happen to know each other.
Oh my god.
We'll get them on at the same time, bro. Anyway, that's all I got to say.
Okay,
But any of the hard questions, any science-based stuff, any questions of the universe, philosophy, and things like that, we're getting this guy on.
Good.
Yeah.
Put them in the comments and I'll answer them too.
Exactly. Yeah. So, well, that being said, thank you, Peter, for being here and taking the time out of your day. It's been an absolute pleasure. We hope that you do come back after seeing it. And then when you see the final cut of this episode, you'll really decide if you want to come back.
I actually don't really enjoy watching myself on video too much, but I'll do it. I'll do it for you. And I just want to say, I really enjoyed this. Thank you both for having me. Look forward to coming back another time.
No, well, ladies and gentlemen, and everyone in between, thank you for joining us on another episode of the Bobby Sox Show. We are your hosts, Alan and Ash, and our guest. It's applause again for Dr. Peter. How do you say it?
Oh, I say halat, but halat's fine.
Yeah, halat. See you guys on the next one.
Awesome. Thank you so much. That was great.
No, thank you.